This part of physics, we are going to talk about sound in general, and we'll go into points that are related to sound, like velocity of sound, sharpness of sound, loudness, the level of the sound. Also, we'll talk about Doppler effect and the resonance in tubes. Okay, I'll start by a question. If a person A is here and person B is here, and person A produces sound, so the sound has a speed. When it goes from point A to point B, it has a speed, and the speed, it means how many meters can the sound travel, or the waves of sound travel, in 1 second. Okay, if this place now, it happens in cold weather, and also same, it happens with the same distance, but in what? On hot weather. So which area the speed of sound will be higher? It's gonna be hot weather. Because when the hot weather, as we know, when you heat particles in general, their kinetic energy becomes higher. That means their movement or their velocity will become higher. So that means particles now, each particle can transfer the sound waves to the other particles faster than cold weather. And in general, this is now related to the velocity of sound. So velocity in sound in general is 343 meter per second. This one, if the Celsius degree is 20 degrees. If the weather is 20 degrees. Okay, what about if the weather is 25 or 30 degrees or more? So in this case, so for 20 degrees, the speed or the velocity of the sound is 343 meter per second. Okay, if the temperature is, for example, 21 Celsius, so that means if it increases by 1 Celsius, what will happen for the velocity? The velocity will increase. Will increase by what? It will increase by 0.6 for every increase in 1 Celsius. So that means if 1 Celsius increases, that means the speed will increase by 0.6. Okay, if 10 Celsius increase, so that means instead of 20, it becomes what? 30 Celsius. In this case, 10 increases. So that means 0.6 times 10, which is what? 6 degrees will increase. So that means the velocity of the sound will become 349 meter per second. I hope you understand now what is the velocity of the sound and what depends on. So the velocity of the sound depends mainly on temperature. Okay, now we go to another point, which is the sharpness of the sound. What does the sharpness of the sound mean? We're gonna see it now. So here, for example, now we have 3 types of sounds. This sound that is produced, and here the sound is produced, and here the sound which is also produced. Okay, the sound when it is produced here, it's gonna be, as you see, less number of wavelengths per second. For example, as you see, wavelength, less number of wavelengths per second are moving. So that means this is a slow motion of waves. So number of waves that are moving per second is less. That means this one is low frequency. Okay, what about the second one here? As you see, it's medium frequency. And what about this? What about the sound here of a whistle? This is a sharp sound. It's classified as sharp sound. And sharp sound is like a whistle, like birds chirping, like breaking glasses. These sounds are classified as sharp sounds. Sharp sounds means higher frequency or high pitched sounds. but these ones are low sound. Here it is low frequency, so that means low, which is the opposite of what? Sharp. So these ones now, how any sound, it can be sound of people, how can we differentiate between the sounds? It depends sometimes how sharp or soft this sound is. How sharp or how soft, it depends what is the frequency of the sound, which is how many rotations the speed of the or the waves of the sound move per 1 second. So you have soft and you have sharp sounds, and we understand now the examples of them. Okay, what about, so you understand now what is sharpness of the sound and what does it depend on. So the higher the frequency, the sharper the sound will be. The lower is the opposite. Okay, what about the loudness of the sound? When the sound is loud or not loud or weak. This is now depends on the amplitude of the what of the sound. So for example, here now the amplitude from here to here is small. In this case, the sound is not loud. So the loudness, being loud or weak sound, it depends on the amplitude of the sound, not the frequency. Not the frequency. So sometimes you hear this one now, you hear the whistle by using this instrument. You hear it weak sound, but it's still sharp. It's still sharp. And sharp sounds, you didn't feel them fine to your ear. You didn't feel them quiet to your ear in general when you hear them. So you understand now the difference between sharpness of the sound and loudness of the sound. And you understand that sharpness of the sound depends on the frequency of the sound, while loudness of the sound depends on the amplitude of the waves of the sound. Okay, what about sound level now? How we know, how we measure the sound level? We measure them by using a unit called decibel. So this decibel now is the unit that we use it to measure what? The sound level. So you understand now sound frequency and what this is affected by. We understand sound sharpness, and you understand sound loudness, and also you understand how to measure the level of the sound. Okay, we'll go now to the second main point of the lesson. Okay, before now, we explain Doppler effect, which is the second point. We need all to listen to this sound. Okay, the question now, where was the sound changed of the fire truck? Where was it changed? Related to the person who was photographing here or taking the video, where was the sound of the fire truck changed? Okay, if we repeat it now, we're gonna see that exactly at this point, the sound is raised. So that means when the source of the sound is coming to you, you hear the sound differently from when the source of the sound is moving away of you. So that means at that point, when the source of the sound started to change from the direction that is coming to you to the direction that is going away of you, there is here change in sound. And this is now what we call it Doppler effect. So Doppler effect now is the change in sound, but it changed in what? It changed in loudness? No, it is a change in frequency. It changed in the frequency. And when we say change in frequency, that means a change on the sharpness of the sound. So that means the sound before before it passes the person here in this case, the sharp used to be soft. That means not sharp. Then when it comes to you exactly at the point that is coming to you, in this case you call it what? Sharp. Okay, we're gonna explain it here by showing this photo. So in this point exactly, when the person was here, and the ambulance or whatever is the source of the sound is coming to the person, so that means as you see here, you're gonna see the frequency here like many rotations per second. So that means condensed here. So that means the rotations of the waves will be a lot per 1 second. In this case, it's gonna be higher frequency. But if the observer is here, as you see here now, there is a space between what? Between the rotations. So that means it takes long time to take more rotations per second. That means less number of rotations per 1 second. So that means this is lower what? Frequency. Lower frequency. So that means it depends on the observer and the source, and also what? The speed of sound and the speed of the source. Okay, we're gonna explain now what is related to what? To the formula. Okay, we are going to talk about this part here exactly. We are going to talk about this part. So in this part now, we have a source of sound, which is the ambulance here. And we have a listener here, observer or detective, we call him. So we have a source of sound that produces sound. And the sound itself, when it moves with a speed or with a velocity. So the velocity of the sound, we call it V. The velocity of the sound, we call it what? V. And here now, the source itself, which is the speed or the velocity of the car, of the ambulance here, is called with a velocity, we call it V of sound, of source. So that means the source velocity. And now this person now, maybe he is moving at this time. While he is listening, he's moving. If he is moving or she is whatever, that means he is moving in what? In velocity, we call it what? Velocity of the detective or velocity of the what? Of the observer. So either V, D or V, O, it's the same. So that means we have 3 types of velocities here exactly. Now, how many frequencies do we have as well here? How many frequencies? Now, there is a frequency that when the sound is produced, at the time it is produced, it's produced with a frequency that is called the source frequency. Now, this frequency will be changed when it comes to the what? To the observer. So the observer now will listen to a frequency which is F of observer, FO, or F of the detective, which is what? FD. So how many variables here we have? We have 5 variables. These 5 variables are linked together in one equation. What is our goal? The value of the frequency that the detective will listen. So that means FD. So that means F of the detective here, it's going to be equal to F, which is the frequency of the source, times, here you write fraction. Then here V, which is the frequency, which is the velocity of the sound itself, minus the velocity of the detective, then over V minus velocity of the source. So this formula is the formula to find the frequency that the detective will listen. The detective on the video or in the sound we heard to was the person who used to record the scene. He was here, the detective or the observer. So what is the sound that he listened to? By using this formula, we get the frequency here again. So now, this formula now, when it is made based on that the direction of the velocities are the same. How? So in this case now, it means the observer is moving in velocity to the right, and the source is moving in velocity to the right, and also the sound is moving in velocity to the right. So that means the three velocities are on the same direction. So if the three velocities are moving in the same direction, you apply this formula as it is without it changing the signs of the variables. That means VD will remain VD and the sign of it negative here. The sign that is here is negative. Okay, when do I change the sound? Okay, always classify the velocities based on the sound velocity. Based on the sound velocity. What do we mean based on the sound velocity? That means now the sound velocity to the right. Okay, if the sound velocity to the right and the other velocity is to the right, so we apply this formula as it is. Okay, what about, for example, now if the observer was moving left? In this case, when you go back to the formula here to apply it, we classify the velocity is based on the velocity of the sound. So the velocity of the sound was right. So that means velocity of sound, I keep it as it is. Always this V, which is of sound, we keep it as it is. Now, V of the detective, is it same direction or opposite direction of the sound velocity? In this case, it's going to be opposite direction. So in this case, you need to change this negative to be positive. And now we go to VS. Is VS now moving the same direction of the V? Yes, so keep it as it is and then to change the sign, the sign. But if it is now in opposite as well, in opposite direction, so that means in this case, if it is in opposite direction to the sound velocity, so you need to go to change the negative here to be positive. So again, you need to memorize this formula as it is, with here minus and with here what? Minus in the denominator and the numerator. And this one is when all the directions of the three velocities are on the same direction of sound. So if any velocity is in the opposite direction of the sound, wherever the sound velocity is. So if one of them is in opposite direction to the sound velocity, or both of them are in the opposite direction of the sound velocity, so we need then to change the sign here based on the opposite velocity. So you understand now what is Doppler effect, and you understand what is the change in sound, and you understand what is the formula and how we can apply the formula of Doppler effect. And you're going to solve questions related to Doppler effect on the next quiz. Okay, now we go to the third point. Okay, on this point now, we are going to talk about resonance in closed pipes and open pipes. How? For example, here in this experiment now, we have here a tuning fork. And when this tuning fork is vibrated here upside down, it will create a change on the pressure of the particles of air here. So this change now will produce like a sound, or they'll move like sound. And these ones now, they'll move inside and here to the water level here, and they can come back. And you can adjust by using your hand, you can adjust this tube up and down till you get a sound. Not all the time you'll get the sound. At a specific height, for this column, you get what? Sound. Okay, the first sound you're gonna hear it is exactly when the length of the tube, the length from here to here, is exactly quarter lambda. So that means this part, as you see it here, this one is what? Is called quarter lambda. So when the length of the tube is quarter of lambda, we're gonna listen to the first resonance or the first sound here. Okay, then when it's gonna be the next sound? This is now for closed tubes. What do we mean by closed tubes? That means one part of the tube is closed. So that means here there is no opening. So that means only one opening that is up. There is no opening down. So that means these ones, we call them here closed pipes, or one end closed pipe. So the first resonance or the first sound, you will hear it exactly when the length of the tube is quarter of a lambda. Okay, this is now the first one. So that means first one when it is quarter of a lambda. Okay, what would be now if I can adjust the tube another time and I make it longer? Will I hear another sound? Yes, you will. And third and fourth. The second one, you're gonna hear it now by adding just half a lambda. So this one is quarter lambda. So that means when will be the second resonance? When you add half a lambda plus quarter, you're gonna be what? 3/4 of a lambda, which is this one. Now, what will be the third then resonance? It's gonna be when the length equals what? Add also half a lambda. It's gonna be 5 over what? Over 4 lambda, which is this one. It's gonna be like this shape as you see. Here it means 1 lambda and quarter. So that means 5/4 of a lambda. While here it's exactly 3/4. Here it means half lambda and here 1/4. So here it means half lambda and here what? Quarter. So that means 3/4. So the first resonance in closed tube, and you need to memorize that perfectly. You need to memorize this idea perfectly. The first resonance of the closed tubes happens when the length of the tube is quarter of a lambda. Then the second one will be 3/4, then 5/4, then 7/4, and so on. So the first one to memorize it is very important. Okay, what about if the tubes are open? Open, that means open from both sides. Same idea. But here what you need to remember is that the first harmonic or the first resonance, you're going to hear it when it is exactly half lambda, when the length is half lambda. So this one starts from quarter lambda, while this one starts from half lambda. While the second one now, you keep adding half. You keep adding always what? Halves. Here the same, you keep adding what? Halves. So just you memorize the first resonance, the first harmonic in closed pipes, quarter lambda. In open pipes, half a lambda. Then keep adding halves for every next harmonic. So that means here, if this one is half lambda, when you add half, also it's gonna be 1 lambda. Then if you add half, it's gonna be 3 halves, which is 3/2 lambda, and so on for open pipes. And here we understand it for what? For closed pipes. So these ones are important then to tell you what is the velocity of the sound. Velocity of the sound, velocity in general of any wave equals the frequency times what? Times lambda. So when you find the lambda from the length here, you find the lambda, then you multiply the frequency, you get that the velocity of the sound. So you understand what is related to sound and Doppler effect also, and resonance in tubes. Then we're gonna go to solve questions related.